Hi, today I'll be giving you a brief introduction on how radiation was accidentally discovered by a man named Antoine Henri Becquerel. Becquerel was a French physicist from Paris and he was around 44 years old when he discovered the radioactivity of uranium. In the year 1895, X-ray was discovered by Wilhelm Conrad Röntgen. Becquerel's discovery of uranium's radioactivity was kind of connected with the discovery of X-ray. He wanted to prove that uranium produces X-rays, but he later on admitted that his conclusion was wrong and that uranium produces something different than an X-ray. A little background about Becquerel. He was born into a family of physicists. Both his father and grandfather held a position in applied physics in an organization in Paris. He's always been interested in fluorescence and photography. This is because his father was actually an expert in fluorescence and photography, which influenced him as well. Becquerel heard about the X-ray discovery in a meeting at the French Academy of Sciences. From then on, he began looking for a connection between the phosphorescence he had been investigating and the X-ray. To prove this connection, he did an experiment. In this experiment, he had a hypothesis, and that was if uranium salts were to absorb sunlight and emit X rays, it would be visible on the photographic plate. So he wrapped a photographic film with black paper since it's sensitive to UV. Then he placed the crystal uranium salts on top of the wrapped photographic film. He then placed objects such as coins on the photographic plate and found he could produce outlines of those shapes. He concluded that uranium could emit penetrating radiation similar to X ray. However, he was wrong. After his experiment, he left the uranium crystals and wrapped photographic plates in a dark drawer. The result of this made his earlier conclusion wrong. The images on the photographic plate were very clear. He later concluded that uranium emits radiation of its own, unlike X rays. And that's the story of how radiation of uranium was accidentally discovered. Other very important people in the history of nuclear chemistry are a couple. They are Marie and Pierre Curie. Marie is of Polish citizenship and she met her husband Pierre in the University of Paris, where he also works at. Pierre Curie is the head of the laboratory at the School of Industrial Physics and Chemistry. And there he diligently works on his research about crystals and magnetic properties of bodies at different temperatures. However, when Marie Curie heard of Becquerel's discovery, she decided to investigate this mysterious uranium rays. Based on her investigation, thorium actually produces the same rays as uranium does. She also realized that the strength of radiation did not depend on the compound, but on the amount of it being used. Marie and her husband then studied natural ores containing uranium and thorium, and this is how they discovered two new elements called polonium after Marie Curie's country of origin and radium after the Latin word for ray. Now that we know the history of nuclear chemistry, we can now differentiate the differences between chemical reactions and nuclear reactions. So, for chemical reactions, atoms are rearranged by breaking and forming of chemical bonds. An example for that is the formation of water from the reaction of hydrogen and oxygen. Hydrogen and oxygen are covalently bonded and they share electrons. Now we can look at the nuclear reaction, wherein elements or isotopes of the same elements are converted from one to another. These elements are called transuranium elements. They are mostly synthetically produced due to their short half-life. These transuranium elements are transuranic elements or elements with atomic number greater than 92. For the second differences, we can look at the chemical reaction. Only electrons in the atomic or molecular orbitals are involved in the breaking and forming of bonds. An example of that are the bonds we are more familiar with, like chemical bonds, covalent bonds, ionic bonds, and others. Those bonds uses valence electrons. Meanwhile, it's a different story for nuclear reactions. Protons, neutrons, electrons, and other elementary particles may be involved. An example would be the beta minus decay, wherein a neutron decays into a proton and an electron and an antineutrino. Now let us look at more differences between chemical reactions and nuclear reactions. At number three, um, for chemical reactions, we have reactions are accompanied by absorption or release of relatively small amounts of energy. An example of that would be the neutralization reaction. The overall reaction is actually slightly exothermic. However, the temperature change is negligible in diluted solutions. For nuclear reactions, however, reactions are accompanied by absorption or release of tremendous amount of energy. An example would be the nuclear fission and the nuclear fusion. Another example is for the chemical reactions in number four, which is rates of reaction are influenced by temperature, pressure, concentration, and catalyst, which is a totally different statement when compared to the nuclear reaction, which states rates of reaction normally are not affected by temperature, pressure, and catalyst. Now let's talk about the nuclear transmutation. Nuclear transmutation is the conversion of one chemical element or isotope into another. In other words, atoms of one element can be changed into atoms of another element by transmutation. Natural or spontaneous transmutation occurs in unstable radioactive elements. These elements will be transformed into a stable element over a series of decays or decay chain. For example, uranium 238 or 238 transmutes spontaneously into lead 206 through a series of steps. So, when it comes to transuranium elements, however, these are chemical elements with atomic numbers greater than 92. So, namely, they are neptunium, plutonium, berkelium, and nihonium. So, now we have a question. The question is, which of the following is a characteristic of a nuclear reaction? Letter A, new element is formed. B, valence electrons of atoms participate in the reaction. C, the rate depends on external factors. D, no new element is formed. So the correct answer was actually letter A, new element is formed, which is a characteristic of nuclear reaction.
In this part, we will be discussing radioactive decay and its types, as well as how to balance nuclear reactions. An atom is stable if the forces among the particles that make up the nucleus are balanced, and an atom is unstable or radioactive if the nucleus has an excess internal energy caused by a surplus of either neutrons or protons. Radioactive decay is the emission of energy in the form of ionizing radiation. This spontaneous and irreversible process happens when an unbalanced atom called radionuclides loses one or a combination of particles. The radioactive decay law states that the number of parent nuclei in a radioactive sample decreases exponentially over time. As time progresses, the amount of parent nuclei decreases very rapidly. Every radionuclide has a specific decay rate measured in terms of half-life, which pertains to the amount of time it takes for one half of the radionuclide to decay. Half-lives can be of mere seconds or hundreds to even billions of years. When a radionuclide decays, the number of protons in the nucleus changes. Hence, it transforms into a different atom, and the resulting atom is also called the decay product. Majority of radionuclides only decay once before becoming stable, while some decay in more than one step and are called series radionuclides. The series of decay products created to reach this balance is called the decay chain. The products within the chain are always radioactive except for the final stable atom. Elements are distinguished by the number of protons, neutrons, and electrons that they possess. Each chemical element has a defining and same number of protons and electrons, yet the number of its neutrons can vary. As we know, atomic number is the proton number and mass number is the total of protons and neutrons. Atoms with the same atomic number but different mass numbers are called isotopes. They share almost the same chemical properties but differ in mass and therefore in physical properties. Isotopes are also what we call the atoms that are involved in radioactive decay. Radioactive isotopes are the unstable forms that dissipate excess energy by spontaneously emitting radiation in different forms such as alpha, beta, and gamma rays. Here are examples of some significant naturally occurring radioisotopes. After talking about the atoms involved in a decay, let's move on to the types of decay that occurs. First is alpha decay. It is a nuclear process where an unstable nucleus transforms into another element by releasing two protons and two neutrons, or simply a helium nucleus. These particles with a large mass and a positive charge only affect surfaces and can travel far through the air or dip into solids. Next is beta decay. Beta decay occurs whenever an unstable nucleus transforms and releases particles to become more stable, and there are two types of beta decay: beta minus and beta plus. Beta minus decay happens whenever a nucleus has too many neutrons. A neutron is transformed into a proton and an electron, with the electron being ejected. To ensure the rules of particle physics, an antineutrino is released, and on the other hand, beta plus decay comes from a nucleus with too many protons. A proton is transformed into a neutron and a positron, then again to ensure the rules of particle physics, a neutrino is released. Next, we have gamma decay. It is a type of radioactive decay that occurs when a nucleus undergoes a transition from a high to a low energy state. This process differs from alpha or beta decay as it does not release charged particles but instead releases a high-energy gamma ray photon. Gamma rays are highly ionizing photons with no charge or associated mass, and undergoing gamma decay does not alter the structure or composition of the atom. To undergo gamma decay, a nucleus must be in an excited energetic state similar to the excited states that electrons can occupy in atoms. If a proton or neutron in the nucleus jumps to an excited state, the new daughter nucleus must release energy to allow the proton or neutron to relax back to the ground state. This transition results in the emission of a gamma photon. Another way for the nucleus to achieve stability is by positron decay. This increases the number of neutrons and decreases the number of protons. The atomic number Z decreases by 1 while the mass number A remains the same. Positron emission occurs when a proton in a radioactive nucleus changes into a neutron and releases a positron and an electron neutrino. Positrons are the antiparticles of electrons. Therefore, a positron has the same mass as an electron but with the opposite charge. Last are neutron and proton decay. Neutrons decay into a proton, electron, or an antineutrino, while protons decay into a positron or a neutral pion. Now that we have learned about the types of decay, we'll tackle balancing nuclear reactions. Again, nuclear reactions occur when a nucleus emits particles or rays. In these reactions, atoms are converted into atoms of other elements. Moving on to balancing, just like in balancing chemical reactions, nuclear reactions are also governed by laws of conservation. In this case, conservation of mass number and conservation of atomic number. With that, to say that a nuclear reaction is balanced, equal total number of protons and neutrons and total charges must be observed. To start, consider the following elementary particles: alpha, beta, gamma, positron, neutron, and proton as either reactants or products. Take this reaction of cesium-137 to barium-137 for example. Since the mass numbers on both sides are the same, the mass of the missing particle must be 0. Now that we have a balanced mass number, a balanced atomic number follows. On the reactant side, we have 55, whereas 56 on the product side. To have an equal number of protons, we'll subtract 1 from 56. Hence, the charge of the missing particle is -1. As we know, the particle with a mass number of 0 and a -1 charge is a beta particle. Therefore, the balance reaction is the atoms of cesium-137 are converted to the atoms of barium-137 and a beta particle or an electron, and this reaction undergoes a beta decay. Another example is the reaction of uranium-238 to lead-206 in alpha and beta particles. The reactants and products are complete in this reaction, so to balance this, we'll be needing the appropriate coefficients. First, subtract the mass numbers 238 and 206 and we'll get 32. Then the atomic numbers 92 and 82 and we'll get 10. To get the alpha particle coefficient, the difference of the mass numbers will be divided by the mass number of an alpha particle. This gives us 32 divided by 4 and the quotient is 8. To check, 238 is equal to 206 plus 8 times 4 plus 0. So, 206 plus 32 is 238. With that, we have equal mass numbers. Now that we already have the alpha coefficient, we're left with only one unknown. To get the beta particle coefficient, we will add and subtract the atomic numbers. On the reactant side, we have 92, and on the product side, we have 82 plus 8 times 2. This gives us a total atomic number of 98. For the protons to be equal, 92 is subtracted from 98, then we'll have 6. To check, 92 is equal to 82 plus 8 times 2 plus 6 times negative 1. So 82 plus 16 minus 6 is equal to 92. Finally, the atomic numbers are equal. Therefore, the balanced reaction emits 8 alpha particles and 6 beta particles. For the last example, we have the atoms of polonium-212 to be converted to the atoms of lead-208 in a particle. To balance, again, mass numbers and atomic numbers are subtracted. 212 minus 208 is 4, and 84 minus 82 is 2. The particle having a mass number of 4 and an atomic number of 2 is the alpha particle or the helium nucleus. Hence, an alpha decay occurred in this reaction. As a review, try to answer the following questions. For number 1, the atoms involved in radioactive decay are A isotones, B isobars, or C isotopes. For number 2, this decay occurs whenever a nucleus has too many neutrons, A alpha, B beta minus, or C beta plus. For number 3, what type of decay occurs in this reaction? Xenon 118 to iodine 118 and a positron particle. A beta, B proton, or C positron. And lastly, complete the nuclear reaction. Chromium 53 and an alpha particle to X and a neutron. What is X? A iron 56, B iron 57, or C iron 58.
For the kinetics of radioactive decay, it follows the first-order kinetics, where T is the rate of decay, lambda is the first-order rate of constant, and N is the number of radioactive nuclei present at time t. With a half-life of ln2 over lambda and an integrated rate law of ln nt over n0, which is equal to the negative rate constant times t. Now let's have an example. An isotope of cesium-137 has a half-life of over 30 years. If 1 gram of cesium-137 disintegrates over a period of 90 years, how many grams of cesium-137 would remain? First, what you are going to do is use the equation of the half-life to get the rate of constant, the rate constant, which is equal to 0.023104906. Then, next is to substitute to substitute the rate constant value in the integrated rate law, get the number of nuclei or number of cesium-137 that will remain after 90 years, which is 0.125 grams of cesium-137. Now, dating based on radioactive decay, the half-lives of radioactive isotopes has been used as atomic clocks to determine the ages of fossils and ancient artifacts. One example of that is radiocarbon dating, which uses carbon-14 isotope with a half-life of 5,730 years, and can be accurate in dating for up to 500,000 years. It is produced when atmospheric nitrogen is bombarded by cosmic rays from the Sun. Here are some of the other isotopes used in dating with their corresponding half-lives. The disintegration of a radioactive nucleus is often the beginning of a radioactive decay series, which is a sequence of nuclear reactions that ultimately result in the formation of a stable isotope. This image shows the decay series of a naturally occurring uranium-238, which involves 14 steps. This decay scheme is known as the uranium decay series, also shows the half-lives of all the intermediate products.
So now we will discuss about nuclear stability, focusing on band stability and island of stability. Nuclear stability refers to the balance between the forces that holds the nucleus together, or what we call the nuclear binding forces, and the forces that tends to break it apart, such as electrostatic repulsion between protons. Nuclear stability also refers to the tendency of a nucleus of an atom to decay, which means to change into something else. The isotope of an element, which we call a nuclide, is unstable. The nuclide has the tendency of emitting some kind of radiation and is called radioactive. Radioactivity is associated with unstable nuclides. Carbon-12 is a carbon atom with a total atomic mass of 12. Since carbon can only have 6 protons, carbon-12 must have 6 neutrons. Therefore, carbon-12 is stable. Carbon-14 is unstable because it has 8 neutrons. In this slide, we can see the factors that determines the nuclear stability. First, we have the mass number. The mass number is a count of the total number of protons and neutrons in an atom's nucleus. As for an example, we have hydrogen's 3 natural isotopes named hydrogen 1, hydrogen 2, and hydrogen 3. Each isotope has a different mass number. Hydrogen 1 has 1 proton, so its mass number is 1. Hydrogen 2 has 1 proton and 1 neutron, so its mass number is 2. And hydrogen 3 has 1 proton and 2 neutrons, therefore its mass number is 3. So why is the mass number a factor in determining the nuclear stability? Protons and neutrons in the nucleus are held together by the strong nuclear force, which is much stronger than the electrostatic force, but operates over very short distances. As the size, therefore therefore the mass number of the nucleus increases, the outer nucleons are less tightly bound because the strong force has a limited range. For neutron to proton ratio, the ratio of neutrons to protons in a nucleus is a key factor in nuclear stability. For lighter elements or the low atomic numbers, this ratio is close to 1:1. However, as the atomic number increases, the neutron to proton ratio also increases. This is because the electrostatic repulsion between protons, of which increases with the number of protons, needs to be balanced by the strong nuclear force, which is mediated by neutrons. As for the magic numbers, the protons and neutrons in a nucleus appears to have energy levels as the electrons in an atom have energy levels. The shell model of the nucleus is a nuclear model in which protons and neutrons exist in levels, or shells analogous to the shell structure that exists for electrons in an atom. Filled shells of electrons are associated with the special stability of the noble gases. The total number of electrons for these stable atoms are 2, 10, 18, 36, 54, and 86. Experimentally, it is noted that the nuclei with certain numbers of protons or neutrons appear to be very stable. These numbers are called the magic numbers and is associated with specially stable nuclei. According to this theory, a magic number is the number of nuclear particles in a completed shell of protons and neutrons. For protons, the magic numbers are 2, 8, 20, 28, 50, and 82. Neutrons have the same magic numbers, as well as the magic number 126. In the odd-even rule, when the numbers of neutrons and protons in the nucleus are both even numbers, The isotopes tend to be far more stable than when they are both odd. Out of all 264 stable isotopes, only 4 have both odd numbers of both, whereas 168 have even numbers of both, and the rest have a mixed number. This has to do with spins of the nucleons. When two protons or neutrons have paired spins, or what we call the opposite spins, their combined energy is less than when they are unpaired. The table shows the number of stable isotopes according to the number of protons and neutrons being even or odd. We can see here that only carbon-12 have both even numbers of protons and neutrons, therefore making it the most stable. While lithium-6 both have odd numbers for protons and neutrons, meaning it's the least stable one, therefore making it more radioactive. The band of stability is the region in which nuclides lie in a plot of number of protons against the number of neutrons. The concept of band stability relates to the behavior of atomic nuclei based on their excitation energy. Nuclei can exist in different energy states, forming bands. These bands represent different rotational or vibrational modes. The stability of a nucleus within a band depends on its energy relative to neighboring states. Some states are more stable, while others are less stable. We can see in the diagram in the right side of the slide is what we call the band of stability, and sometimes called as the belt of stability or line of stability. Black jagged line is the most stable region. The straight black line is where proton numbers equal neutron numbers. For the first 20 or so nuclides, the jagged line is very close to the straight line. As nuclides get larger, they need more neutrons than protons to remain stable. So, the jagged line starts getting steeper than the straight line. The nuclei above the belt of stability can lower the ratio and move to the belt of stability by radioactive decay, which converts a neutron to a proton. This increases the number of protons and decreases the number of neutrons and gets the nuclide on the jagged line. The opposite also can happen when the nuclide has too many protons. In this sort of decay, protons are converted into neutrons. The orange part in the graph is what we call the beta plus decay or the positron emission. This occurs when a proton in an unstable nucleus is converted into a neutron, a positron, and a neutrino. This process can only happen if the daughter nucleus is more stable than the mother nucleus. The result of beta plus decay is that the neutron to proton ratio increases, moving the nucleus towards the band of stable nuclei. The blue port in the diagram is what we call the beta minus decay. Beta minus decay occurs when a neutron in an unstable nucleus is converted into a proton, an electron, and an anti-neutrino. This type of decay is common when a nucleus has too many neutrons. The result of beta minus decay is that the neutron to proton ratio decreases, moving the nucleus towards the band of stable nuclei. And lastly, the yellow part in this is what we call the alpha decay. Analysis emits an alpha particle, which consists of two protons and two neutrons. This process is associated with heavy, unstable nuclei. The result of alpha decay is that both the mass number and the atomic number decrease, moving the nucleus closer to the band of stable nuclei. The island of stability is a predicted set of isotopes of super heavy elements that may have considerably longer half-lives than known isotopes of these elements. It is predicted to appear as an island in the chart of nuclides, separated from known stable and long-lived primordial radionuclides. The diagram here on the right side of this slide shows the measured and predicted half-lives of super heavy nuclides. Ordered by number of protons and neutrons, the expected location of the island of stability is around B is equal to 112 or the Copernicum is circled. The key points about the island of stability is the predicted set, the longer half-lives, magic numbers, synthetic creation, locations, uncertainty, and experimental challenges. The mass defect is the difference between the mass of an atom and the sum of the masses of its protons, neutrons, and electrons. It results from the binding energy released by the formation of the atomic nucleus. According to Einstein's theory of relativity, the mass of a system measures the total energy of the system. Thus, when a nucleus is formed, some of the mass is converted to energy, resulting in mass defect. The mass defect can be calculated by subtracting the actual atomic mass from the sum of the mass of protons and neutrons present in the nucleus. We can see the formula here in this slide, where delta M is the mass defect, Z is the number of protons, and N is the number of neutrons. Nuclear binding energy is the energy required to separate an atomic nucleus completely into its constituent protons and neutrons. It is the energy equivalent to the mass defect. The binding energy can be calculated using Einstein's formula E is equal to mc squared, where E is the energy, m is the mass, and c is the speed of light. The nuclear binding energy can be calculated by converting the mass defect into energy using the formula that is attached in this slide, where E sub B is the nuclear binding energy, delta M is the mass defect, and c is the speed of light. In this slide, we can see the practice problems that are prepared by yours truly. We will predict of which is the radioactive in each of the following pairs. You can pause in this part of the video if you need more time to answer these questions. So here are the answers in the last slide.
Good day. I am Krisha and I will be discussing nuclear fission and nuclear fusion, the energy and its impact. Okay, let's first discuss the nuclear fission. It is the process in which a heavy nucleus, which mass is greater than 200, divides to form smaller nuclei of intermediate mass and one or more neutrons. Because the heavy nucleus is less stable than its products, this process releases a large amount of energy. We can also correlate this nuclear fission to Einstein's theory of relativity. The equation E is equals to mc squared is highly relevant to nuclear fission and fusion processes, as it describes the conversion of mass into energy and vice versa. Two German chemists known as Otto Hahn and Fritz Strassmann worked together and discovered nuclear fission. So what they did was they bombarded uranium-235 with slow neutrons, and whose speeds is comparable to that of air molecules at room temperature. Under this temperature or conditions, uranium-235 undergoes a fission, and they have observed that this heavy um, isotope can be further divided into isotopic components. The first application of nuclear fission was in the development of the atomic bomb. The crucial factor in the bomb's design is the determination of the critical mass for the bomb. A small atomic bomb is equivalent to 2,000 tons of TNT, or also known as trinitrotoluene. Because 1 ton of TNT releases about 4 times 10 raised to 9 joules of energy, 2,000 tons would produce 8 times 10 raised to 13. And the mass of the isotope present in a small bomb must be at least 1 kilograms, as shown in the equation. And for obvious reason, an atomic bomb is never assembled with the critical mass already present. Instead, the critical mass is formed by using conventional explosive. So we have here the nuclear reactors, and we have three, which are light water reactors, heavy water reactors, and breeder reactor. The basic principle behind nuclear reactors is to control and utilize the heat produced when heavy atomic nuclei, typically uranium-235 or plutonium-239, undergo fission. A peaceful but controversial application of nuclear fission is the generation of electricity using heat from controlled chain reaction in a nuclear reactor. Currently, nuclear reactors provide about 20% of the electrical energy in the United States. This is a small but by no means negligible contribution to the nation's energy production. Several different types of nuclear reactors are in operation, and we will be discussing. First is the light water reactors. Most of the nuclear reactors in US are light water reactors. An important aspect of fusion process is the speed of the neutrons. Slow neutrons split 235 nuclei more efficiently than do fast ones. Because fusion reactions are highly exothermic, the neutrons produced usually move at high velocities. For greater efficiency, they must be slowed down before they can be used to induce nuclear disintegration. To accomplish this goal, scientists moderators, which are substances that can produce kinetic energy of neutrons. A good moderator must satisfy several requirements. It should be non-toxic and inexpensive, as very large quantities of it are necessary, and it should resist conversion into radioactive substance by neutron bombardment. Furthermore, it is advantageous for the moderator to be a fluid so that it can also be used as a coolant. No substance fulfills all these requirements, although water comes closer to many others that have been considered. Nuclear reactors that use light water or just simply the H2O as moderator are called light water reactors because the H1 or the proton is the lightest isotope of the element hydrogen. Another type of nuclear reactor that uses deuterium oxide as moderator rather than H2O. Well, deuterium absorbs neutrons much less efficiently than does ordinary hydrogen. Because fewer neutrons are absorbed, the reactor is more efficiently and does not require enriched uranium. The fact that deuterium is less efficient moderator has a negative impact on the operation of the reactor because more neutrons leak out of the reactor. However, this is not a serious disadvantage. The main advantage of heavy water reactor is that it eliminates the need for building expensive uranium enrichment facilities. However, D2O or the deuterium oxide must be prepared by either fractional distillation or electrolysis of ordinary water. The last example of a nuclear reactor is the breeder reactor. A breeder reactor uses uranium fuel, but unlike a conventional nuclear reactor, it produces more fissionable materials than it uses. Um, a typical breeder reactor or nuclear fuel containing uranium 235 or plutonium 239 is mixed with uranium 238 so that the breeding takes place within the core. For every uranium 235 or plutonium 239 nucleus undergoing fission, more than one neutron is captured by uranium 238 to generate plutonium 239. Thus, the stockpile of fissionable material can be steadily increased as the starting nuclear fuels are consumed. It takes about 7 to 10 years to generate the sizable amount of material needed to refuel the original reactor and to fuel another reactor of comparable size. This interval is called the doubling time. Another type of a nuclear reaction is known as nuclear fusion. And in contrast to nuclear fission process, nuclear fusion, the combining of small nuclei into larger ones, is largely exempt from the waste disposal problem. This behavior suggests that if two light nuclei combine or fuse together to form larger, more stable nucleus, an appreciable amount of energy will be released in the process. This is the basis for ongoing research into harnessing the nuclear fusion for the production of energy. Another is that fusion reactions takes place only at at a very high temperature, and they are often called the thermonuclear reactions. And we can also correlate nuclear fusion to the Einstein's theory of relativity, and energy released in nuclear fusion is immense in this process that powers the sun and other stars. A major concern in choosing the proper nuclear fusion process for energy production is the temperature necessary to carry out the process. Some promising reactions are shown here in the slide. These reactions take place at extremely high temperatures on the order of 100 million degrees Celsius to overcome the repulsive forces between the nuclei. The first reaction is particularly attractive because the world's supply of deuterium is virtually inexhaustible. The total volume of water on Earth is about 1.5 times 10 raised to 21 liters because the natural abundance of deuterium is 1.5 times 10 raised to negative 2%. The total amount of deuterium present is roughly about 4, 4.5 times 10 raised to 21 grams or 5.0 times 10 raised to 15 tons. The cost of enriching deuterium is minimal compared with the value of the energy released by the reaction. In contrast to the fission process, nuclear fusion looks like a very promising energy source, but although thermal pollution would be a problem, and the process produces little radioactive waste, if a fusion machine were turned off, it would shut down completely and instantly without any danger of a meltdown. In test runs, a number of laser beams transfer energy to small fuel pellet, hitting it and causing it to implode. That is to collapse inward and all the sides and compress it to a small volume. Consequently, fusion occurs like the magnetic confinement approach. Laser fusion presents a number of technical difficulties that still need to be overcome before it can be put to practical use on a large scale. An application of fusion reaction is for the hydrogen bomb. The technical problems inherent in the design of a nuclear fusion reactor do not affect the production of hydrogen bomb, also called as thermonuclear bomb. The objectives is all power and no control. Hydrogen bombs do not contain gaseous hydrogen or gaseous deuterium. They contain solid lithium deuteride or LID, which can be packed very tightly. The detonation of hydrogen bomb occurs in two stages. First, a fission reaction and then a fusion reaction. The required temperature for fusion is achieved with an atomic bomb. Immediately after the atomic bomb explodes, the following fusion reactions occur, releasing vast amounts of energy. And now we will be discussing the uses of isotopes. Radioactive and stable isotopes alike have many applications in science and medicine. The first one is the application of isotope in photosynthesis. The overall synthesis reaction can be represented as 6 moles of carbon dioxide reacting with 6 moles of water, producing glucose plus 6 moles of oxygen. The vital or significant radioactive isotopes that can stimulate photosynthesis is carbon 13 and oxygen 18. And one also that impacts the process or the reaction is the carbon 14 present in carbon dioxide 14. And it was possible to isolate the intermediate products during photosynthesis and measure the amount of radioactivity of each carbon containing compound. Well, in this manner, the path of carbon dioxide through various intermediate compounds to carbohydrate could be clearly charted. Isotopes, especially radioactive isotopes that are used to trace the path of the atoms of an element in a chemical or biological process, are called tracers. Tracers are also used for diagnosis in medicine. For example, sodium 24, a beta emitter with half-life of 14.8 hours, injected into the bloodstream as a salt solution can be monitored to trace the flow of blood and detect possible constrictions or obstructions in the circulatory system. Radioactive and stable isotopes are employed in medical imaging, cancer treatment, and research. And another example is technetium-99, a radioactive isotope that is widely used in nuclear medicine for single photon emission computed tomography or SPECT. This isotope helps visualize and assess organ function, blood flow, and identify abnormalities. Before we move forward to our last topic, let's first have a assessment. So, kindly answer this problem. In a fusion reaction, which of the following isotopes is commonly used as fuel in experimental efforts to achieve controlled nuclear fusion for energy production? A. Uranium 235, B. Plutonium 239, C. Deuterium, and D. Carbon 14. If your answer is C. Deuterium, your answer is correct. Deuterium is an isotope of hydrogen with one proton and one neutron in its nucleus. It is a common fuel for experiment efforts to achieve controlled nuclear fusions for energy production, especially in the United States. Deuterium is abundant and can be extracted from water, making it a practical and accessible fuel source for fusion research. Uranium 235 and plutonium 238 are primarily associated with nuclear fission. Meanwhile, carbon 14 is a radioactive isotope that is used in dating archaeological and geological samples. Thank you. As for the last part of our discussion, I will be discussing the biological effects of radiation. And if you're not well aware of the damage it causes to us humans and also to animals and other biological systems, well, it causes two main uh, two main damages known as genetic damage and somatic damage. Somatic damage refers to damage that occurs in the cell of an organism's body, excluding the reproductive cells. It has long been known that exposure to high energy radiation can induce cancer in humans and other animals. Cancer is characterized by uncontrolled cellular growth, growth, but on the other hand, it is also well established that cancer cells can be destroyed by proper radiation treatment. In radiation therapy, a compromise is sought, and the radiation to which the patient is exposed must be sufficient to destroy cancer cells without killing too many normal cells, and it is hoped without inducing another form of cancer. Another is the genetic damage, which involves alterations or mutations in the DNA sequence of an organism's germ cells, either sperm or egg, potentially affecting the offspring. It also means inheritable changes or gene mutations. For example, a person whose chromosomes have been damaged or altered by radiation may have deformed um, offspring. And that would be all for my presentation, and thank you for listening to our group.